changed since then? And many things have remained the same. Things that changed is that, for example, we used to use floppy disks. Those hard, small things like this to plug into the computer, and then sometimes it doesn't work, and then you lose your files. We actually use these also sometimes to submit our solutions. The IOI, you got a floppy disk, and at the end you were supposed to upload the executables of your codes to the floppy disk, and this was tested. In the actual ICPC, they used to have these with runners, so you wanted to submit those. This is a computer network. We talked about this already before my day, but I did take part in one competition where this actually happened. So again, you upload your stuff onto the floppy disk, you gave it to a runner who physically brought it into the other room. So in the ICPC finals, everybody knows the balloons. They're pretty colorful and they're a fun way of getting reward and solve the task. Well, this is only the current part of this tradition. The original motivation to have those balloons is that there was no online rank list. You couldn't see online on the web server how the other teams are doing. So that's why the balloons were invented as a way to convey this information. So back in the very old days, the balloons were there just to show you that yes, these ones are doing well, and also by looking at the colors and having the color sheet that red is problem A, you knew the essential information you should have as a contestant, which is the easy problem you are missing. So if somebody was everybody is already solving problem A, and you think it's very difficult, then you should probably go and reread the problem statement and think about it some more. This should be something easy you are missing. So things change, the competitions evolve. If you look at the contest problems from 20 years ago, they are much easier. They are not necessarily easier, but they are different. They focus on different parts of the spectrum of ancient algorithms. It used to be the case that more of the problems are of an implementational nature. It used to be the case that there was a bigger focus on, for example, brute force search and pruning thereof. And nowadays, you don't see many such problems. The focus is shifting, expanding. The areas of focus of these programming competitions are somehow becoming more clear, more well-defined. This is not necessarily a bad thing, but it changes the game somehow. It used to be the case that nobody knew what to expect at the IOI as well. A major change in this was the IOI in '97 in South Africa, which was very different from all the previous ones in that they couldn't really come up with good, exact algorithmic problems. What they did, the entire IOI was a bunch of optimization problems. Find a random program that will find as good a solution as possible, and here's a scoring function. And this took people by surprise because they didn't expect such a type of problems, they didn't prepare for such a type of problems. Somehow again it introduced changes, also in the IOI, it led to the introduction of the scientific committee as some kind of international body which should oversee the proper preparation of tasks. Later on, already when I was also involved in the ISC, there came the need to come up with a syllabus, to kind of somehow write down a set of topics. This is something you might expect, this is something that is definitely out of scope. And the necessity for this came from the power creep, let's call it. That is, people are trying to do harder problems to challenge the best contestants. Then they will be bringing in more and more topics, and many of them require knowledge that is already taught only at the university. A famous older example of this is that calculus as such is forbidden at the IMO, the Mathematical Olympiad. And this is done completely intentionally to limit the scope of those problems. So there is an unwritten rule, there shouldn't be an IMO problem where knowing calculus gives you an advantage. This is just to draw a line somewhere. This is the knowledge we still want the contestants to have, and this is something they can postpone for later, just to define the rules of the game better. The IMO has already measured it this way, so if you take a look at the IMO problems from 20 years ago and now, they will be roughly of the same difficulty. There are easier years, there are harder years, but roughly it stays on the same level. If you go 50 years ago, the IMO problems will be also easier and a bit different. So for mathematics, it's already converged to some stable state. They found the limits, they found what is the best way how to run these competitions. We are still getting there in computer science. Both the IOI and the ICPC and many other international competitions are still evolving. One of the things you can see, for example, if you look at the brochures of the ICPC, they have this chart showing how the contest grows. And each year there are more and more students, and if you go 20 years ago, the number of students was 3,500, and now it's 40,000 taking part in the yearly rounds, and it's still growing. And if it's still growing, it means you get more and more better contestants as well, because, well, you have the bell curve of like problem-solving abilities. The people who take part in these competitions anyway tend to be somewhere on this side of the spectrum. And if you take 10 times as many people, well, you will get 10 times as many people in each of these tennis leagues. And then, if you are the problem setter for such a contest, you have to challenge them. You have to come up with problems that are still a bit harder, take a bit more time, take a bit more thinking, a bit more experience. And it's a very hard thing to do right. So this is still the current state of these programming competitions. The fact that they are getting bigger necessarily means that they will still be getting a bit more difficult. And the difficulty can come from the problems themselves. So there can be problems that are difficult to come up, more difficult to come up with the correct idea. There can be problems that are harder to implement. And then there can also be the difficulty coming from the set of topics. So there can be very many different topics covered by these competitions, and the spectrum, the scope is still also growing and being adjusted a little bit. So this is our current playground. We have a bunch of talented people like yourselves, and personally I still do compete from time to time. I don't have a lot of time to do so. I like to at least take part in the Code every year and maybe one or two other contests if I have the time. But mostly I see myself as already being on the other side of the barrier, as being one of the problem setters and one of the people who are trying to do something on this leading edge of these competitions to try to come up with the best ways to challenge these top contestants. You may have heard about the IPSC contest we are doing at our university. So this is the Internet Problem-Solving Contest. The last edition, which was year 19 of this contest, took place 2 days ago. And this is like our personal playground to try different wild stuff that couldn't make it into real competition. If you are running, for example, Google Code Jam, then your goals are to make a very good contest that is fair to everybody and that is somehow reasonably solvable and contains problems you can prepare for. And you may not be inclined to do wild experimental stuff there because if you're a company like Google, your main goal is to use this as a way to attract people and then to hire them. And the IPSC is something like, well, I often take problems that didn't fit in anywhere else, and we just throw them there and have some fun with them. So, if you haven't heard about this contest, its website is this, and there's an archive of past problems, and I encourage you to look at those because there are some really good gems of competitive programming there. And in this last competition, we managed to have a problem set that was almost perfect for such a competition. Well, among the problem setters, the usual criteria for such problem set would be that, first of all, there should be no bugs. So if you, during the contest, have to reject a task because you screwed something up, it's not a really good problem set. Second of all, everything should be solvable. So ideally, you want to see each of the problems is prepared solved by someone. But on the other hand, nobody should be able to solve everything in time. We actually managed to do this by the smallest possible margin. So the winning team, it was the tourists, the two other guys. They were missing one subproblem at the end, so we were very happy that yes. This is a very hard thing to do because judging the difficulty of tasks that are these and the respect of the tasks that are designed to be very hard but not impossible. This is something that can only be done with an insane amount of experience and an insane amount of luck. Yeah. You have very little data to actually use when judging the difficulty of these problems. This is also the case why the ICBC World Finals try to have as many people as possible go through the tasks and so on. The IOI in the last years is trying to do some kinds of beta testing for better calibration before the actual contest. Okay. So these are the programming contests we now have. And the main question I now have is, why do people take part in these? What do we gain from doing these programming contests? What are the main reasons? And it's kind of hard to answer this completely. For instance, for me, one of the main reasons obviously was fun. If you are not having fun while doing this contest, you are doing something wrong, and you should probably stop and find something else that interests you. Because the fun is somehow necessary for it to be something you want to spend your time on. And for me, it was fun because I love to learn, and I love to be challenged. I love to compare myself to other people, try to compete against them, try to win. Obviously, winning is a very good feeling. I don't know if you tried it. You should. So, getting to compete, getting to win, getting to have fun solving problems is certainly one motivation. The learning is another motivation, another good thing that comes from these programming contests. And people who, and the things I'm saying now can also be said like in response. Whenever some story about programming contests hits mainstream media, if you open the discussion, you'll see a lot of people who have zero experience with it just read the article and then come with their opinions like, alright, this is completely useless, and in practice nobody will ask you to solve a problem in 2 hours, you will have a month to design your solution, and nobody uses algorithms anyway. And, well, we know better. We know that there is a lot of challenging problems around that do require very hard algorithms. And in order to be one of the lucky few who get to work on those problems, you have to be good at working on those problems. You have to be good at thinking about algorithms and designing them and arguing about the complexities and making sure they're actually correct. And this doesn't come easy, and this doesn't come cheap, and this isn't something you can just pick up by attending a course at the university. This is something that needs hard work, as everything does. And one of the ways of putting the hard work in, and also have fun, is precisely these programming competitions. And people who do these competitions and do well at them, for example, have a much deeper understanding of the algorithms involved. This is essentially for me the perfect way to understand an algorithm. It's not enough to attend a lecture and see the algorithm and say to yourself, yes, I know how it works. You only understand it if you can implement it, if you can actually convince the computer this is what you have to do. And that's still not enough. Not just the implementation. You need to be able to modify the algorithm. You need to understand not just the way the code works, you need to understand the underlying ideas. And when you need to solve something similar but not entirely the same, you need to be able to think about, does this algorithm still apply? Can I modify it? How do I do it? What do I need to change?
in order to make it work. So this is also necessary for you to have a complete deep understanding of an algorithm. And the third thing I usually require is that you should be able to explain the algorithm. This is the last part of the puzzle. So you should be able to sit down with your friend who doesn't know it yet, and you should be able to explain this. Why this is necessary is that once you start explaining something, you will be forced to do it properly. If you are just thinking for yourself, yes, I understand this step, yes, I understand that step, the explanation makes complete sense to me, you may be deceiving yourself. And this happened to me as well many times. I thought I understood it perfectly, then I started to explain it to somebody else, and after the first 3 sentences, the other person had a question. Okay, but why is this true? I don't see it. And at this moment, I was like, well, it's obvious that wait a moment, then after 15 minutes of go, yes, it's really obvious. so this is it. Instead of just looking at the algorithm and having the feeling, yes, I've seen it before, programming competitions give you a motivation to go deeper, to gain better knowledge of these things. And this gives you an advantage, a significant advantage against the rest of the field. And it doesn't matter whether your desired career is somewhere in academia, if you want to be a researcher in computer science, or whether you want to go the more popular route and find a job at a Silicon Valley startup or one of the established companies. All of these ways are facilitated by doing competitive programming and being good at it. Another aspect of these contests is implementation. And this is, again, something where experience matters, because at the beginning, when I was starting with like doing Top Coder and the ICPC and similar competitions, it used to be the case that almost everybody was using C++, and a very popular thing was to have macros. So you had a macro for the for cycle that you just typed the variable once, and then it expanded into the actual for cycle from 0 to -1, and then you had a macro to clear an area of memory, and so on and so forth. And there are people who are using like single-letter variables and no indentation just to minimize the time they needed to type the code. And this also looks scary, and this also looks like a collection of bad habits, because whatever else you do after competitive programming, if you write code this way, everybody else that has to work with you will take you and break your arms so that you won't write any code anymore. And it turns out to be the case that the amount of time saved by doing this in the competitions is not worth the effort. The places where you really save time are, first of all, about certainly thinking about the problems. Coming up with the solutions sooner is much, much more important than any minutes saved while doing implementation. The second thing is debugging. If nobody is perfect, and none of us are able to consistently write code that works on the first try, we aim to do this, we try our best to do this, but nobody is 100% successful. You will need to go back, read through your code, debug it. If you are in the ICPC contest, you only have one computer, you have 3 people. It is often the case, especially during the late hours of the contest, that one person is working on the computer, and the other 2 have a printout with them to debug another solution that is not working at the moment. If you get to this stage, you need the other person on your team to be able to read and understand your code, to be able to go through it and check whether everything works correctly. So writing nice, readable code is, again, a good idea. And another third place where you can save time is spending extra time thinking before going to implement. solution. A very common mistake in these competitions is that as soon as you come up with a working solution, you want to go to sit down with the computer and the keyboard and start typing it in. The thing the experienced contestants do is they spend 2 extra minutes, for example, asking the question, okay, I only know how to solve this task. Can I do it in a better way? Can I do it in a way with fewer special cases? Can I do it in a way that has shorter code? Can I do it in a way where I, instead of analyzing case work, can I use brute force to try the possibilities somehow and still fit within the time limit? So your question is, what is the first solution that comes to my mind that solves the task? Your question shouldn't even be, what is the most efficient way of solving this task? The correct question to ask is, what is the simplest, what is the nicest implementation I can come up with that will solve the task within the given limits? If n is 20 and the time limit is seconds, I can't afford to try all subsets of those 20 items. And if triangle the 2 to the 20 subsets gives me a solution that's easier to write than a solution that would be running in polynomial time, then this is what I should go for. I should aim for finding a solution that's easy to implement, and then it will be a solution for which it is easy to avoid making programming errors. There are many algorithms, for example, starting with the very easy binary search, continuing with something like the KMP string substring search algorithm, that are notoriously error prone. Yes, they can be implemented, yes, they are very efficient, but for example, getting the plus and minus ones everywhere correct is something that's hard and that requires experience. And if you can solve it at the same task using a different approach that doesn't have this property, then it may be a better idea to do so. And if you spend a minute thinking about coming up with a better algorithm, then you can save 10 minutes of debugging your code. And this is where the contests are won or lost. Sorry. Yeah, okay. And this kind of brings me to one of the major points I wanted to make during today's lecture. And this is kind of related again to mathematics. One of the famous mathematicians, Paul Erdős, once said that he believes that God has a book, and in this book, for each mathematical theorem, he has the most beautiful and the most enlightening proof there is. And this notion used to then went on to be known among people as the book, or the proofs from the book. These are the perfect, nicest proofs. And there is actually now a book that is called Proofs from the Book that has some of these nice collection of nice mathematical proofs and arguments. And I believe that a very similar thing to be true for algorithms. It's not exactly the same playground, because in mathematics, if you have a proof, it's either correct or incorrect. If it's correct, then you have solved the problem. If it's incorrect, then you haven't. In computer science, and especially algorithm design, there is one more dimension, which is the complexity. You can have different solutions which all solve the problem, but for example, with a different time complexity or memory complexity or both, or they are different in some other measure. And this is something you don't get in mathematics. You do get a little bit. You get some of the proofs can be constructive, some of them can be only existential. So in some cases, when you want to show that an object exists, you can only show that it exists, but you don't know how it looks like. In some cases, you can even construct such an object and show, yes, it does exist because, yes, this is the kind of constructed. So, but in computer science, we have this broader spectrum, and sometimes the question of beauty is not exactly identical with the question of efficiency. For example, consider the problem of shortest paths in graphs. You have a weighted graph, so some cities, some edges between them, roads of different lengths, and you want to compute the measures of distances from this town to this town, which is the path of this length. And we all know that there is a very efficient algorithm to do so, which is the Foy-Marshall algorithm, which is just 3 nested for loops: for all k, for all I, for all j, trying improving the path between I and j by going from I to k and then from k to j. So 3 nested loops, a single if, and you have a working algorithm. And to many people, including myself, this is beautiful. But at the same time, this is not the fastest way of solving this problem. There are faster ways based on matrix multiplication, and there are even faster ways based on transitive closure and some greedy algebra and stuff like this. So essentially, this is a problem that can be solved in the time equal to the time needed to multiply the matrices. But the other algorithm is very involved. The current best matrix multiplication algorithms are something that is pages and pages of code and has large constant factors. And so asymptotically, it is a better solution, but is it more beautiful? Hard to say. To someone, maybe it is. Somebody, it certainly isn't. And in some sense, the programming competitions are also playing somewhere on the spectrum. And in many cases, in many of the contest problems, the author is trying to show you something beautiful, something nice, and the challenge is not just to look for any algorithm that works, the challenge is to look for a beautiful algorithm. And if you are able to find it, then you are rewarded. You are rewarded with an easy implementation, you are rewarded with being certain your solution is correct, if you have the insight necessary. And this can help you with. That's all there is. Okay, so I think that's enough of like abstract big picture talking for now. And let's get you thinking. Let's get to some actual problems. The first problem I'll talk about will look as follows. So imagine that you have a world that is two-dimensional. It's a unit square grid. As of this board, I don't know whether you can see it well, but I'll try to highlight it somehow. So there are some cells in the world, and we are essentially playing solitaire. So we have some pieces, each piece can inhabit a square, and they can jump each other. So whenever we have a piece, let's call them soldiers. So we have some soldiers, and you can move them as follows. You can pick a soldier and choose a direction, either horizontally or vertically, and the only possible move you can do is you can jump over another soldier, and the soldier you jump over is then removed from the grid. So if you have a soldier, and an empty space, you can jump from here to there and remove this one. So instead of this configuration of 4 soldiers, we would get a configuration like this. So these 2 remain in place, and this one jumps here, and we have a configuration like this. Now this one can jump here, and now there are no more moves possible. Okay, so this is like more or less standard game. There are some single-player puzzles called Solitaire, where you have a configuration of these soldiers, and you have to find a way how to make the jumps so that at the end only a single soldier remains. But now we are going to play a different game. The different game is called Exploring Enemy Territory, and it looks as follows. So there is a vertical line, this is the boundary. To the left of the line is our territory. To the right of the line is enemy territory. We can number the columns somehow, so this will be column 0, this is still on our side, and then now positive numbers 1, 2, 3, 4, 5, and so on are the columns on the enemy side. Now the goal of the game is that before the exploration, we can arrange the soldiers on our side in any way we want. And so we can pick any arrangement of soldiers, distribute them into the cells, and then the game will start, we'll be able to jump, and we are also able to jump into the enemy territory. So in order to explore column 0, which is still on our side, the only thing we need is a single soldier. This was easy. In order to get some soldier into column 1, the optimal solution is obviously to use 2 soldiers like this. So this will be the initial configuration, and then the entire process of exploration goes like this. You jump from here to there, and wow, we have a soldier that reached column 1. Okay. So, now we want to get a soldier into column 2. The question for everybody here, what is the minimum number of soldiers we need to place here? So you need to place some soldiers here, then make some jumps, and your goal is to get a soldier anywhere into the column number 2. So feel free to grab a pen and paper if you have some. If you don't, then just visualize it and try to come up with as good a solution as you can.
Você faz tudo na cabeça. É bom. O tiozinho morre também. Bom, eu consigo fazer com 5. 4 será que dá? 3 definitivamente não dá. Quatro? O cara é bom, mano. Como faz com 4, cara? Só faz. O da mata deu uma. O da mata deu uma definição muito boa para o acampamento. É um lugar onde os maratonistas fingem por 2 semanas que não precisam de descanso e repetem múltiplas vezes a frase "é só fazer".
Você tá falando isso, tá? Será que alguém tá assistindo?
Tem 5 pessoas, eu acho.
Dá pra ver aí?
Dá pra ver no YouTube. Olha, eu vou aparecer na stream.
Tá meio torto, né? Amanhã a gente faz mais bem feito.
E você com a mão na boca.
Então. Eu vou deixar aqui. Porque eu consigo ver a saúde da live. Eu fiz com 4, tio, eu sou uma burra. É porque eu fiz o cara morrendo aqui e eu contei 5. Eu sou mó retardado.
E mais. Eu não faço frente.
Eu tinha pensado nisso. E tinha dado mais 4.
Talvez 8. Eu acho que não pode ver mais 4 ações lá.
3, cara.
Conseguiu?
Não, acho que não dá. Não tem como, velho. Você tem, tipo, um número finito de combinações que você pode botar os três. E ele é bem pequeno.
É, 3 não dá.
Ele é bem pequeno, ele é cheio de simetria. Tem, tipo, uma linha de 3.
Chegar na 3.
Ah, chegar na 3.
Mais 4 também.
Vários 8.
Dá pra fazer com 200. Chegar na 3, depois da 2 e generalizar, cara. Chegar na enésima.
Eu sei que chega na 4, deixa eu ver se eu sei. Porque, tipo, aí a gente meio que só usei do outro lado. Mas eu não tem um do outro lado.
Não, acho que tem um algoritmo idiota, que é tipo, você faz várias linhas e aí você tipo, joga um cara pra baixo aqui. Você vai ter que fazer assim. Eu acho que você não sabe o que tá.
Alright then, show of hands who thinks they have a solution.
Esse cara aí, eu não confio, cara. Eu ia falar que dá pra fazer com 1.
So, how much do you think is the optimal answer? 4. And that's correct. I think the essentially only configuration that works with 4 soldiers is like this. So we build a configuration like this, and then the optimal way of jumping, the first jump goes there. So we have a soldier here, and then this one jumps like this, like this. Okay. So in order to explore column number 2, we needed 4 soldiers. Shall we do one more? Yeah.
Você fez com 8?
Alright, so let's go back. This was the optimal configuration in order to get to column 2.
Parece que 16 não ajuda, né?
Now, for this one, arguing about optimality would be pretty easy because we can do it by brute force. Clearly, 2 is not enough, and there are only a few reasonable configurations of 3 soldiers that have to be examined, and none of them work. So this has to be optimal. For column 3, we don't have the time to go through everything. So let's try coming up with any valid solution. Don't worry about optimality, just try coming up with any valid solution, any one that will work, and then you'll get your soldier to the column number 3. And this time, let's try adding some time pressure. So the first person who will come up with a working solution, I want them to shout at me. Oh, you have it. Okay, perfect. So can anyone come up here and draw a solution that works for column 3?
Ah, é fácil isso. Você só põe mais 4 aqui embaixo, aí pula 2, pula aqui. Mano, esse cara é o germano da gringa.
Alright. Yeah, sure. Go ahead.
So you have I can see the 2. Right, so you need to jump in.
Yep, that's it. Well done. Okay, so this is actually one of the optimal configurations, as you might have guessed. There's another one that looks like this. Instead of having these 2 here, we would have them here. So the other possibility looks like this. So this is the one that will and then this can be either here or here, or obviously here. But in all cases, in order to explore column 3 of the enemy territory, we need 8 soldiers. Now comes another important part of problem solving. Which is pattern recognition. So in most cases, when you see the sequence 1, 2, 4, 8, you know what to expect next. So What's the guess for the next number here? 16. That's wrong. It turns out to be one of the very few special cases when the intuition fails you. And it turns out to be the case that we need slightly more soldiers. We need 20 of them. Maybe they don't fit completely. So here you could put these on one side and then these on the other side. But then we don't have any more sides to put the another 8 on. So we need a little bit more to get them closer. So, yeah. It often works. Often in the ICPC, if you see a pattern like this, it is worth a submit. Just try guessing whether it works, submitting. And if you get a wrong answer, well, it was a quick guess anyway, it doesn't cost you so much. But in this case, well, what wouldn't work, then the pattern is a bit more difficult. So in order to get some soldier to column number 4, we already need 20 of them. And now, let's go to the true intuition testing step. And we will collect the guesses for column number 5. So you have 1, 2, 4, 8, 20. What's the next number? And just shout out your guesses.
36.
Okay, so I heard something lower, like 42 or something like that. I heard you guys that there is no way. Any other opinions? Wow, we are scared. We got burned with a 16 or a scared thing, yes. It turns out to be the case that the most pessimistic guess was right. It's actually impossible. If you want to know a lot more about this problem, the keyword to Google is Conway's Army. And I will now show you the reason why it is impossible. The thing you can do is you can assign some kind of value to these pieces. The farther to the right it is, the more expensive it can be, because you need to spend 2 pieces somewhere to the left in order to produce just 1 piece somewhere closer to the right. Now, the proof will look as follows. First of all, it doesn't matter which cell in column 5 we have to read, so we will just pick one arbitrary. So we will say that this is the goal cell, and we are going to show that it is impossible to reach this particular cell. How do we do this? We will assign a value 1 to this cell, and the values now will be exponentially decreasing for all other cells. So the farther you go from this cell, the higher power of x will be the value of this cell. So this is x to the 3, x to the 4, and so on. And also this cell is x to the 2, x to the 3, x to the 4, x to the 5, and so on. So this one can be seen as x to the power of 0. And any cell now has the weight x to the Manhattan distance from the goal. And now what happens here when we do a jump is that we take 2 soldiers like this, and we jump them, and we only get 1 soldier like this. And when we get to pick the value of x in such a way that if you jump towards the goal, your cost will remain exactly the same, and obviously if you jump away from the goal, then your cost will decrease. So the thing you want to do is, if you have a jump something like this, or like this, so this will be x to the 5, x to the 6, x to the 7. And if you jump from these 2 to this one, the property we want to have is the sum of the cost of these 2 cells with this cell. So we have x to the 5 equals x to the 6 plus x to the 7. Now the obvious choice would be x equals 0, but it doesn't really give us any information. So the other choice is divided this x is non-zero. You get 1 equals x plus x squared. And this is a quadratic equation. And the solution should be very similar, very familiar to you if you have seen Fibonacci numbers and similar stuff. It's essentially the same equation, but reciprocal. So the solution, there is a positive real root, which is 1 divided by the golden ratio. So this is the value of 0.6 over 8 something. The golden ratio is 1 plus square root of 5 divided by 2. So this is something like this cell is worth 1, this cell is worth 0.6, this cell, all of these cells are each worth 0.6, all of these cells are 0.6 squared, and so on. So it exponentially decreases. And now we can easily see that if you have a collection of soldiers, we can sum up the cells where they stand, and whenever we make a jump, the sum will either remain the same if you are jumping towards the goal, or if you have soldiers here and there, and you jump here, then you lost a lot, and you gain only a little, so it decreases. But there is no way for it to increase. And now you can take a look at our half of the plane. What you get here, in this particular row, is x to the 5, x to the 6, x to the 7, and so on. So this is a geometric series. We can actually write down the sum of this series in closed form. And the same is true for each row. This row will start with x to the 6 and go on. And in this particular case, if we actually sum up all of these geometric series and then we get another sum like this, we can actually compute the sum of this entire half plane. And what will we get? The entire sum will be exactly 1. So what this means is that if you take any finite set of soldiers, the cells they cover will have a total value of less than 1. And you have no way of increasing it. So even if you take a million of millions of millions of soldiers, their total value will still be less than the one you need for the target cell in the 5th column. So the next time you see a puzzle, what is the next term of the sequence? 1, 2, 4, 8 can continue 20 and infinity. So this is an example of a result I would consider pretty. And even though this is mostly a mathematical puzzle, it can be also useful for programming competitions because it shows you one possible way of thinking about combinatorial problems. And this is thinking in terms of invariance. This is thinking in terms of, let's find a property that doesn't change or cannot be improved, and this can be then used to show that some kind of solution is optimal. In this particular case, well, this is a famous problem in the name, because the property is very obscure. It was hard to find. It was hard to come up with this way of thinking. But maybe you can try a similar approach on an easier problem, a problem that looks like this. So now we only have the first one quadrant of the plane, and we start with a single pebble in the top left corner. And the only allowed move now is whenever you have a cell with a pebble, you can remove the pebble, but you can only do it if both of these cells are empty, and you have to place 2 new pebbles into these cells. So the first valid move could be to remove this one and replace it by these 2 pebbles. Then you could remove this pebble and place 2 pebbles here and there. And at this moment, you are not allowed to remove this pebble because you don't have an empty cell to the right. So first, we can have to get rid of this one, and then we can remove this one and replace it with 2 pebbles like this. And what I managed to do now is that this diagonal is empty, And also this diagonal is already empty. I pushed the pebbles far down. And the question for you, which I will not answer now, and you can think about it now, is whether it is possible to clear arbitrarily many diagonals, or whether we will get stuck at some point. So what is the maximum number of diagonals you can clear? Think about it, try to come up with a suitable invariant.
Sempre tem uma mais pra baixo. Sempre tem uma na última diagonal. Mas isso não quer dizer que você vai ficar com a diagonal livre, né?
So I think I've been talking here for about an hour. I think it's a good time to take maybe a 10-minute break and we will continue.
Aí você pode, se você travar
Você
uma...
fica numa só.
Não, você pega uma só e manda pro pai.
Você pode mandar. E aí você pensa igual que você quiser. Aí você pode mandar todo mundo. Ah, não, pode.
Não, porque vai começando a crescer, né? Porque ela duplica. Grande Victor. Ele é só o responsável pela live stream, né? Mas acho que eu vou colocar ele mais pra frente, porque ele tá com a...
Produção aqui. Beleza, cara. Perfeito.
Será que fica melhor, só?
Vamos dar uma arrumada agora. Tirar essas cadeiras aqui, né? De baixo.
Pega aquela cadeira.
Pra saber se com esses movimentos aí principalmente um negócio mais alto.
Liberar.
Pedrinhas em todas as casas de mesmo.
Não, contrário. Não ter. Tipo, porque você nunca volta, né? Então, mano, você limpa uma diagonal.
Como que é? Você começa de um bagulho só e daí você bota...
Você tem um jogo, você começa. É o quarto do plano, aí você começa com uma pedrinha. Aí você pega. Uma pedrinha aqui no corner. Aí você pode fazer um movimento que é: remove a pedrinha e coloca duas nas adjacências dela. Adjacência aqui. Pra baixo e pro lado. Você só pode fazer isso se estiver livre. Aí você pode repetir esse movimento para novas pedrinhas. E aí, eventualmente, você vai liberando diagonais. O primeiro movimento vai liberar a primeira diagonal, e se tem umas movimentos que liberam a segunda diagonal. Aí a pergunta é se tem um limite de diagonais que você consegue liberar ou se consegue arbitrariamente liberar.
Tá razoável, será?
Acho que tá. Eu queria ver a live stream. Tipo, assistir ela. Então, você colocou, tava bom. Deixa eu ver se tem alguém comentando alguma coisa do YouTube.
A gente tá live, né?
Tá.
Olá, pessoal do YouTube.
Bom dia.
Meninas.
Hoje a gente vai falar sobre problemas e soluções bonitas.
É honesto isso. A gente tá realmente improvisando tudo aqui.
Tá torto, né? Tá bem torto, tá?
Mas acho que você tá tentando botar sua mão reta no ar e você tá... Tem que estar de baixo, né? Isso não vai ajudar.
Mas tava menos torto naquela vez. Aqui, ó. Esse negócio aqui tipo, tinha que ficar mais assim, ó.
Beleza?
O áudio está muito bom.
O cara
Falou. É que tipo, o áudio faz sentido tá ruim, né? Até porque qualquer conversa que tiver aqui vai estourar tudo. A gente tem que ligar o microfone aqui. Eu acho que dá, o cara falou que dá.
se a gente não fizer isso hoje, a gente faz amanhã.
E se eles fizeram alguma coisa pra fora?
Não dá, porque o que a gente tá pegando é o microfone do computador e o áudio da caixa.
Ah, e será que ele não vai ajudar, não? Aquela tela.
O que é isso?
Aquele lá que você comprou, aquele vagabundo lá.
Não tem como.
Porque ele é com fio, cara.
É.
Ele vai destruir o computador dele.
Dá uma mandada ali.
Não, mas ele falou que o cara falou que dava pra ligar aquele bagulho lá.
Mas não, o que ele fazia ele tinha falado sobre tipo, cara, tem que usar 2 minutos.
Como eu disse, eu tava tentando. Bora colar lá 10 minutos.
O áudio tá meio ruim? Ou... É,
Legal.
é, sim, é só amanhã que a gente vai fazer alguma
Tá
coisa.
tudo certo.
Tá falando
Tá
que o áudio
funcionando,
tá
mas o
não
áudio
está
tá
ruim.
ruim. Mas a gente pode até melhorar mais. Inclusive, estão ouvindo tudo que você tá falando.
Ou não, né? Porque o áudio
Olha,
é muito bom, então talvez eles não estejam.
Não, mas dá pra ouvir. Não é que não dá pra ouvir, a gente... Quer ver, ó, vamos lá fora.
Vamos lá fora fazer o quê? Ah, tá.
Gente, tá do lado do bagulho. Isso aqui.
Eu não sei. É mó difícil desenhar essa porra, porque você tem que ficar apagando as coisas anteriores.
Faz no computador. Tá funcionando? Ó, você que tá sentado aqui agora, fica de olho, tá tudo torto. Mas fica de olho pra fazer assim, tá ligado? Se precisar. Eu acho que não vai precisar. Tá? E não derruba essa merda. Tá bem torto essa mesa, velho. A gente pega uma mesinha.
Vocês mudaram a parada?
Parece que tá fazendo merda.
Ah, você instalou o Free, o Open Source? Sério? De todos que você testou?
Não, isso é mais famoso. É o que o pessoal usa profissionalmente.
Ah, a gente baixou esse.
É que a câmera parece que é boa nesse teste.
Okay, so after next break, we can now continue, and we'll continue by looking at more problems, looking at more algorithms, talking about stuff. So, one of my favorite things when thinking about explaining algorithms are metaphors. And metaphors are, in general, a very important tool in education. Essentially, it's just like saying, hey, think X, you don't know yet, is similar to think Y, you already know. This is the parallel, and then this is how you can now think also about the other thing X, and this will help you understand it faster. It's all connected to how we learn. One of the things about our learning is that, well, it comes from evolution, it comes from years of living in the wild and having to deal with stuff. And we are built in such a way that the main way we learn is we learn by repetition. If you are trying to do something multiple times, you are getting better at it. You are getting some practice and you are being more focused and so on. You learn. If a child learns to walk, he doesn't walk on the first attempt. It needs several falls and trying to experiment how to gain balance. And it is very much the same with problem solving. It's very much the case that whenever I encounter a problem that uses some new idea, I might be able to solve it. Sometimes I won't. And with many ideas, it was the case that I failed to solve the problem. I gave up. I read the solution in the editorial, and then I saw, oh, this is some new idea I haven't seen before. I haven't solved any such problems. So let's read the solution. So I read it in detail. And I thought, oh yes, this is a nice technique. I understand it. Then 2 or 3 months later, I'm solving the contest, and there is another completely different problem I cannot solve. And I fail to solve it. And then I look at the editorial, and it says, well, you use this technique. I did see this technique, why didn't it come up? I didn't have enough experience. I only had what is called like a separated model. I knew how to solve this particular task, but I didn't know how to generalize. I didn't know, I didn't have enough information to make an abstraction, to make something that would be more general applicable in multiple situations. And this is also how learning works in general. Right? Like the child will first learn that 2 candies and plus 2 candies is 4 candies. Then they will learn that the same goes for toy cars or something like that. Then they will learn that it works for fingers. Then if you have like 2 candies here and 2 candies there, then you can just add the fingers together and there have to be 4 candies. And only at some later point, with enough of these individual experiences, the child is able to make the abstraction, the shift to the higher level, to realize that there are actual numbers and that 2 plus 2 is always 4, regardless of what you are counting. And it only goes the same with all these harder or difficult concepts. You need to have enough individual experiences with a new algorithm, with a new problem-solving technique, in order to be able to actually like completely grasp it, make it your own, and be able to use it, adapt it in other situations. And this is where the metaphors help, because they kind of help you cheat a bit. They can help you take experience you already have with other things and use it in this new context. To give you a concrete example, most of us have practical experience with physics, like in terms of if you take this chalk, and now if I let it go, we have experience, we know what will happen. It will not hang in the air, it will not levitate away, it will fall to the table. So there's gravity. Gravity works, and everybody has already played with some balls and some strings, and we know how it works if you have two balls connected to the string, and you grab one, and you let the other one go. If there is a string, it will not fall down like this. The string will carry it like that, and it will be a simple pendulum. If you just hold the ball with them here, the string will look like this. If you let the ball go, then it will stabilize like this, very easy. We can visualize it, we have practical experience with it. Can this help us design algorithms? Well, sure it can. So imagine you have a graph. And this is the standard weighted graph, cities and roads between the cities, distances. So this is like 17, this is 12. There's some very long road here which takes 141, and so on and so forth. And one of the very traditional problems in computer science is the shortest path problem. I mean, I'm in city A, I want to be in city B, what is the shortest path? And during this lecture, we have already mentioned the Floyd partial algorithm, so you can solve it in n cubed time by finding all pairs shortest paths. You can solve it slightly faster with matrix multiplication. There are also even faster algorithms, notably there's Bellman 4, where you go through the edges, and this is n times m. There is Dijkstra's algorithm, which can be n squared if you implement it just with cycles, or it can be n times or so Dijkstra's algorithm can be something number of edges times a logarithm of the number of vertices if you implement it with a priority queue, or there is also this theoretical result that if you do it with some special data structure called the Fibonacci heap, then you can do it in m plus n times log n time. So this is the optimal time complexity for Dijkstra, but this is something you would actually implement in programming competition. Just out of curiosity, how many of you have already implemented this version of Dijkstra's algorithm? Excellent. Alright, so you know what I'm talking about. But now, if you have this as an actual physical balls and strings model, what is the time complexity of finding the shortest path between A and B? Well, essentially, it's constant time, because what you can do is you can grab ball A into one hand, you can grab ball B into the other hand, and you can pull them apart. What will happen is the strings will become tight, and the shortest path is actually how far you will be able to pull them apart, because at this moment, all of the strings that form the shortest path will be tight, and they will not let you pull those balls apart any farther. So you just grab the two of them, pull them apart as far as they go, and once you get stuck, you have the shortest path. So, in constant time. Why does this matter? Because you can not only use this to find the shortest path from A to B, you can use this for a very similar observation to find the shortest path from a single chosen vertex, vertex A, to all of the other vertices at the same time. Well, we don't have enough hands, obviously, but you can do gravity, you can let gravity do the trick for you. So the only thing you need to do with a physical balls and strings model in order to find the shortest path is grab one of the balls, ball A, and let the entire gadget hang from the ball A. And what will happen there is that the gravity will try to pull all of the other balls as far down to the ground as it can, and the strings will prevent this from happening. So some of the strings will be tight, like this. Some of them will hang like this. Those are the ones that are unused by any of the shortest paths. So the entire gadget, if you hang it by the ball A, will look something like this. Now the strings that are tight belong to some of the shortest paths. The strings that are loose are not used by the shortest paths from A to any other vertex. Why does this matter? Well, because this is essentially Dijkstra's algorithm, or to be more precise, the entire idea of Dijkstra's algorithm is to build this gadget from the top to the bottom. You may have seen the textbook explanation of Dijkstra's algorithm. We have a set of vertices that are already final, we have a priority queue of vertices that are not final yet, and then there is this proof that when we take the vertex with the shortest, the smallest value out of the priority queue, it cannot improve because to pass through other vertices and so on and non-negative edge lines. So this one has to be final, we have to bring into the other set. Well, in terms of balls and strings, this translates directly to a very simple physical argument. At the beginning, the only thing we know is that the ball A is hanging somewhere here, we are holding it, and we know nothing else about the rest of the graph. So right now we can imagine this as not having any of the strings, which means that all of the balls are down here at the bottom, which means plus infinity distance. And now the only thing we are going to do, and this is essentially the idea of Dijkstra's algorithm, whenever we process a vertex, we add the new strings, the strings from this vertex to the other vertices. So now when we will be processing A, we will be adding these three strings, and this particular ball will be hanging somewhere lower because right now this is the best string we have. And now the only observation we need in order to prove correctness of Dijkstra's algorithm is that whenever we are adding a new string between two balls, only two things can happen. One of the things is that the string will hang loose, and we will never use it not even in the future. The other possibility is the string will pull the lower ball closer to the higher ball. So if the new added string is shorter than this distance, this ball will be pulled higher. But obviously it cannot go above the altitude of the other one. So there is no way to pull this ball here by adding a string between these two. And that's everything we need. Whenever you have a ball, if you are adding the strings only from this ball and below, nothing will ever go higher. So the only thing you need to build this gadget is just go from the top to the bottom, and whenever I encounter a ball, add all strings from this ball to the other ones. That's it. So this is the entire idea, and this is also the entire proof of correctness. If we build the gadget in this way, we will never have to go back, as long as all the strings obviously have positive lengths. If you have a string of length -3, it's kind of the physical metaphor breaks apart. If the edge lengths are positive, then we can just visualize it like this and have a deeper understanding. Why do I say we have a deeper understanding? Because, well, you could have understood the original proof of Dijkstra's algorithm, but then somebody comes up with a question, okay, now we have a different problem. You don't only have the original graph, but there can be some new queries. Then some of the edges change in the graph, and in particular, they become shorter. So imagine a country in which they are improving the highway system. So at some point in time, they will take the road and build a new highway that is faster. And the question is, how do the shortest path lengths from the capital change? If one of the roads changes, what exactly is the part of the graph we need to recompute? And here with this visualization, it becomes quite obvious. Well, if this is this one string is the one that gets shorter, the thing that will happen is that it may decrease the distance to the bottom wall of the string, and this can pull to get, so there will be other balls hanging on this one, and some of them will also be pulled higher in the graph if we pull this one closer to the top. So the part we need is to recompute the locations of these ones. So this means running another iteration of Dijkstra's algorithm, but just starting from this ball and stopping whenever the things start to improve. So I really like this balls and strings visualization very much because it somehow gives us a better understanding of what's going on. I have one more example with this, which is again a very traditional graph problem. So this time we will have just a tree. The tree can even be weighted, but for simplicity right now, let's assume that it's not. And the question is, what is the longest simple path in this tree? And we know that there are multiple algorithms to solve this problem. One of them is like do some iterations, and each iteration you discard all of the leaves. At the end you will be left with just a single vertex and just two vertices connected by an edge. This is called the center of the tree, and every longest path has to go through the center somehow, and then you can reconstruct it by going backwards in time. But there is also a very simple but tricky solution to this problem, which was as follows. You start with any vertex A. You come to the distances by a simple breadth first search or something, and you pick B, any vertex that is farthest from A, and then you do the same thing once again, so but starting at B. So starting at B, you can then compute the distances from B to the vertices, and take C as the anywhere the vertex farthest from B. And now magic, the vertices B and C are the endpoints of the longest path in the tree, one possible longest path in the tree. So why is this the case? How can we prove this easily? So imagine that you already know in this tree the endpoints of the longest path. If there are multiple, let's choose just one of them. So for example, this would be X and this would be Y. So far there is no connection with this algorithm. We'll get to it later. So far just we have a tree and we choose one particular longest path. And again, as in the previous example with Dijkstra, imagine that these are balls and strings. Now we need both ends. So we grab X, we grab Y, we pull them apart as far as we can. So X is here, Y is here. This is the longest path in the tree between them. And what does this mean that this was the longest path? It means that now the rest of the vertices, some of them are here, and those that aren't here, they are hanging like this. Somewhere from the path, so it looks like the strings Incas use for writing, the kipu. There is one string like this, and then all of the others are hanging downwards. And now, this being the longest path, it means that something like this cannot appear, so we cannot have just two vertices here and three vertices there, because then from X to here will be longer. So we can visualize it like this. All of the other vertices have to be located inside this triangle. So if you take three steps here, then you must take those 3 steps outwards. And now we can easily visualize what happens in this algorithm. We can pick A as any vertex, and now the farthest vertices away from A are where? Well, the only way to go from A is either stay here, which is short, or you can go to the top, and then one of these directions is better. So with our laws of generality, A is in the left half, and then the vertex farthest away from A is this one, and also anything that lies on this diagonal, but those are symmetric because, well, we can swap it like this and make any of them being this vertex. So if this is the first vertex, the farthest one away is one of these, and for all of them, the farthest vertex away is again this one, and therefore the algorithm works. So very simple visualizations of some balls, some strings that will give you a proof. Okay, are we happy with this? Okay, where do we go next? One other interesting area we can now take a look into are greedy algorithms. Greedy algorithms are excellent because they are usually, if a problem does have a greedy algorithm, the solution is very easy to implement, very short, and very efficient because we just need on each step to make a local decision. What is the best thing to do right now? We do it, and by repeating it, we solve the entire problem. The main risk with greedy algorithms is that many of the problems you will encounter in competitive programming have solutions that are very simple, very pretty, that are greedy, and they are incorrect. So it's very easy to deceive yourself into thinking that you solve the problem. Well, I don't have the proof, but it should be clearly optimal to sort them by this property and then process them in order. Then you submit it, and you get the wrong answer, and you debug it. You find 2 actual bugs in your code, so you resubmit it, but you still get the wrong answer because the algorithm is incorrect. So there is a huge strategy aspect when it comes to greedy algorithms, because sometimes it is actually the best strategy to just trust their intuition, to code it up and submit it. For instance, like it's the last online round of Google Code Jam, and the first problem seems to have a greedy solution. Well, you can spend time proving this solution, but if it actually works and you spend the time proving it, then it will be too slow. There will be 150 other people who will save the 15 minutes by just guessing and submitting. So maybe it's a better strategy to just implement it, submit it with the easy sub-problem and see whether it worked or not. If it did, then you can also run it for the hard one. If it didn't, then back to the drawing board and let's look for a proof. But quite often, the best strategy is not to guess at the greedy algorithm, but to try to come up with a greedy algorithm using a technique that will also give you a proof, that will also lead you to choosing the correct property and give you the certainty you need that I'm not wasting my time, I'm not implementing something that actually works. And there are 2 very simple techniques that both can be very, very powerful in designing greedy algorithms. And I will, again, show them on very simple examples, but then I may give you some pointers to how to apply this to higher problems. So, in order to look at the first technique, let's start with a very, very simple problem. So, so imagine a small village, and there is no water source in the village. There is only a small spring that is at the side of the village, so it pumps out water at constant rate, and the villagers get water by going there with the buckets. So one morning it happened to be a morning when everybody wanted to cook Sunday dinner or something, and so all of the villagers met at this spring at the same time. So we have a bunch of people who have buckets with different volumes. Volumes are V1 to Vn. And the question is to choose an order in which these people should take water into the buckets. Well, in order to choose, well, one possible order would be like just do it in an arbitrary way because we don't have anything to optimize. So what is the thing we might want to optimize? Well, one of the things we might want to optimize is waiting time. So one person will obviously get the water immediately, so they are happy because they can go home and don't care about anything else. But the other people will have to wait. So for each person, we can take their individual waiting time, which starts at 0 and ends at the moment when they start filling in their bucket. And the thing we want to optimize is the mean waiting time. Now we can ask the question, what is the optimal order in which they should fill the buckets that optimizes the mean waiting time? And why? Not just what is the order, but why this is the correct order, why they should do it like this. So, any opinions? So we can sort it by volume and start from which one? From the smallest one or from the largest one? Smallest, largest. Well, measures this for the smallest one. Okay, so there are n factorial different permutations of buckets. Yeah?
Could you fill a bigger bucket and use it to fill another smaller bucket?
Does it help?
Well, maybe because then you can fill two buckets at the same time. While the big one is filling the smaller, there is another person. Maybe, I don't know.
Well, think about it more. You propose something, then try thinking about it. Try. Is it really better? You have to spend the time filling the large bucket with water anyway.
Yeah,
so you could, during that same time, fill first the one of the small buckets, then the second small bucket. The intermediate bucket doesn't seem to help. It also seems to be a very bad idea to switch between buckets. So fill half of one bucket, then half of another bucket, then go back to bucket number one. Because the only thing you get is that both of them have to wait longer. So clearly the optimal strategy is just fill one bucket, go away, fill another bucket, go away. Still leaves us with n factorial different permutations. We suspect that the optimal solution is to just go from the smallest to the largest bucket. How do we prove this easily? And now, the main trick here, and the trick that can be used in any greedy algorithm where you are looking for the optimal order of things, the optimal permutation in which to do it, is that instead of looking at the global picture, instead of looking at what happens on the global scale with all of the n people, we just need to look at two consecutive people and ask the question. So okay, so here is one particular list of buckets. Goes like this. When exactly does it pay off to swap two consecutive people, to consecutive operations? And this is a very important question to ask, because one thing that is always true is that in the optimal order, you don't want to swap anything. So the optimal order has the property that each pair of consecutive elements is in the right order. So if you want to have the optimal order, you cannot have a pair of consecutive elements that are swapped. And you can start looking for a greedy solution by looking at this particular property, by examining when this is true. So what happens in our particular problem? What is the mean waiting time? The mean waiting time for those people is the waiting time of person 1 plus the waiting time of person 2 plus the waiting time and so on, divided by n, which is the number of people. Now, regardless of which order we choose, the number of people, the number of buckets, stays the same. The value n is a constant. So dividing by n doesn't matter at all. So instead of optimizing the mean of waiting times, it's easier to think about optimizing the sum of waiting times. It's exactly the same thing. So this new value is the old value multiplied by n, which is a constant. And now how do we actually visualize the sum of waiting times? So we can visualize each bucket as an interval. So this is like intervals on the time axis. The larger the bucket, the longer it takes to fill it. And this can be one possible order of buckets. So there is medium bucket, a large bucket, a small bucket, and then another largest bucket. And now what are the waiting times? One person goes home immediately, another person waits like this, another person waits until this moment, another person waits until this moment to start filling in their buckets. We could also count the time of filling the bucket into the waiting time, and we wouldn't change anything because we would just count each bucket once. So the sum of these lengths is what we are trying to optimize. And now it should be pretty obvious what happens if we swap two consecutive buckets. So here are some people, person X, person Y, and there were some people before them, and there are some people waiting after them. Now if we swap the order in which these two people take water, it is completely obvious that it will not influence anybody from this group. This group will already be gone by the time these two get to the spring. The other thing that's almost as obvious is that swapping these two will not influence these people. Because anyone who is in this group has to wait both for this one and for this one, regardless of their order. So the only thing that changes are they. In the current situation, one of them can start filling the bucket here, and the other one can start filling the bucket there. But if we were to swap them, if we were to do it like this, then one of them would start here, and the other one would already start here. So this is what we would save from the sum of waiting times. So for these two consecutive people, we can argue that they should be in the order, first the smaller bucket, then the larger bucket. So what we have just shown is that in the optimal solution, there is no case that looks like this, something, 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 larger bucket, smaller bucket. And now we are lucky. This is the place where we actually realize whether or not the problem is solvable completely. Because sometimes it can be the case that the condition you will get is not so nice. And in particular, in some problems, the condition will not be transitive. So you can, if you have A and B consecutively, you want to have A and then B. If you have B and C, you want to have B and then C. But sometimes in some problems it can be the case that you would prefer to have C before A. And in those cases, you will not have a greedy solution. But in our case, we do. We know that it never pays off to have a larger bucket before a smaller one. We can always swap them. So if you have any permutation in which there is a larger bucket and then a smaller bucket, anywhere in the permutation, it's not optimal. And there is only a single permutation that doesn't have this property, which is the permutation from the smallest bucket in sorted order all the way through the largest bucket. So, a very easy thing to think about: when does it pay off to swap two consecutive elements? And the very strong result with a very easy proof, we can see that there is a greedy solution and that we can do it by simply sorting these things. Okay, so this was trivial because, well, the problem was chosen to be as simple as possible and to have this property. So I will now give you a less trivial application of this trick. Yeah. The new problem goes as follows. You have a collection of pieces of paper and each piece of paper contains some string. Now what we want to do is we want to concatenate all of these strings, so put all of these pieces of paper into a single line in such a way that the result should be lexicographically minimal. So once again, the task here, you are given a collection of strings, and among all possible permutation of these strings, find the lexicographically minimal concatenation. So, again, it seems to be a very trivial problem, because, well, in this case, you will first want the string that begins with an A, then you want the C, and then you want the F. And, well, where's the problem? So, if you encounter this problem in programming competition, and I did already said it in some, there is always a large group of people who say that, well, this is trivial. Just take the strings, sort them, there's no one's code, so have a vector of strings, sort the vector of strings, concatenate them, output, submit. 5 minutes, wrong answer. Wait, what? 4 lines of code, there is no way there is a bug in this implementation. And there isn't. The implementation is correct, the idea is not. Why is this the case? It can get tricky because you have 2 pieces of paper and one of them has AA and the other has AAF. Then the optimal solution is AAF. Everything works. But if you have 2 pieces of paper, and one of them has XX, and the other has XSF, they will still be sorted in this order. The sort would leave this one first, and this one later, because, well, this one ends earlier, as a prefix. But the optimal order suddenly becomes XSF, XX. This is better than having XXX, XF. So we got tricked, sorting doesn't work. Maybe this problem isn't solvable greedy. And now this illustrates the power of the technique I was talking about. Because we can still ask the question we asked before. When exactly does it pay off to swap 2 strings? So, given 2 strings X and Y, is it sometimes better? Which one of these 2 is better? But it turns out to be the case that this property happens to be transitive as well. So what we can do now is you can say that X should be to the left of Y, so this is like a curly less than sign. If and only if xy is less than yx. So instead of comparing x to y using the standard string comparison functions, we'll compare xy and yx. So this is a new order of strings. It's not the same order as the lexicographic one, but this is an order, and it can be shown that this new order is also transitive. So it does have the property that these 2 things together imply that x should be to the left of z. This is not easy to show. It takes some casework. Essentially, the only cases that matter, the only cases that are not trivial, are situations where x is a prefix of y, and also y is a prefix of z, because in all other cases you have 2 strings, and they already differ at some position, then this difference will be enough to make this order identical to the original order, and then you can also already say that it's false. So we only need to analyze the cases when these are prefixes of each other, and there it can be shown that the only thing you have, like, there is some basic string, and this is some copies of it, and this is some copies of it. So showing that this new order of strings is transitive takes a bit of work, but it happens to be true. This means that this problem does have a very easy to implement greedy solution, but it's by far not the obvious solution. So what you need to do is you can implement this as your custom comparison function for strings. So you have a function that takes two strings and returns x plus y is less than y plus x. And then you sort your array of strings, but with this custom comparison function, and then you concatenate them. So it does work, but discovering the right sorting order is very much not trivial. And this is the payoff we get. We have learned a new trick. Just look at two consecutive elements. Think about when does it pay off to swap them. And if this property happens to be transitive, then you get a greedy solution. And it doesn't have to be very obvious. One more example for this particular trick would be a problem that has been used in Topcoder Open, I think in 2014. The problem had one more layer of complexity in it, because there was some place where we had to make decisions, which I will skip, but after getting through this first layer of difficulty, we're left with a problem that looks as follows. You have a spaceship, a rocket, and there are n different engines you can use, and each engine has two parameters, xi and yi. And what they mean is that if you turn on this engine, it will run for yi seconds. And while the engine runs, the rocket will be accelerating at a constant rate. And after the interval, the speed at the end will be will increase from the original speed by xi. You can only use one engine at a time, and the question is, what is the optimal order in which you should use your engines to get as far as possible? So, obviously, the total time of using all engines will be the sum of all yi. So, regardless of the order you choose, the total time of using the engines is always the same. Your final speed will always be the same. It will be the sum of all xi. And the only question is in which order to use them to maximize the distance traveled during this part, during the period of acceleration. And again, this may not be completely obvious because now we have two arguments, xi, yi, and it may be solvable greedily, but what is the exact thing we should sort by, or what is the exact criterion of choice? Which engine is better? Is it better to have an engine that increases xi by a lot, but it takes a long time, or maybe something else, some function of x's and y's? And instead of just randomly guessing the correct order, we can approach this problem by maybe drawing a picture and asking again the same question. So again, we have a problem in which we should choose the optimal order of doing things. So it has to be the case that any two consecutive engines have to be in the right order. So for any two consecutive engines, we can ask the question, when exactly does it pay off to swap them? And this is very easily seen with the geometric interpretation. So what we can do is we can do a plot. The x-axis is time. The y-axis is our speed, velocity. And what is the distance traveled? Well, we know the distance traveled is the integral of the velocity over time. So if we draw some kind of curve, so this was our velocity over time, and distance traveled is this area below the curve. So this is what we are trying to maximize. And now each of the engines brings us somewhere. So at the beginning, we are stationary. So at time 0, our speed is 0. And each of the engines, if you have at some time t1, some speed v1, what will happen is that in time t1 plus yi, your new speed will be increased by xy. So this is the change done by an engine. This is yi and this is xi. So if you choose one particular order in which to use the engines, you will get a polyline that looks like this. And now swapping the engines somehow changes this polyline, but these vectors are fixed. So each of these vectors is a vector xi, yi, one of the pairs given in the input. Okay? And now we see the power of this question of asking when does it pay off to swap two consecutive engines? Because it's very easy to see if you have two engines like this one and this one, and you use them in the other order, you will get something that looks like this. You will get to exactly the same point because this is this point. So this was x1, y1, and this was x2, y2. Then you will get to this point, which is this point plus y1 plus y2, or this point plus y2 plus y1 in this direction, and in this direction again is this plus the two x's. So nothing changes here, nothing changes there, and the only difference is that if we use those two engines in the other order, this is the area we gain. So the other order is better. In other words, the optimal order should be such that we never turn left. The optimal order should be convex. In other words, the optimal order is to take all the vectors and take them in sorted order according to the slope. What is the slope? The slope is the value xi divided by yi. So this turns to be the acceleration per unit of time. So by doing this argument, by drawing the picture, by thinking about when to swap two consecutive vectors, here we still choose to swap these two again because this is still concave. We come up not just with the correct property, not just with the correct value to use for sorting, but also with the proof. If you use any two engines in the incorrect order, first the one with the smaller slope, then the one with the larger slope, you will not be optimal, because swapping these two is always better. And it happens to give us a property we can readily use as a sorting key. Just compute the acceleration for each of them, sort them according to acceleration, and then you have the optimal solution. Now, in order to explain why this was asked in the top quarterfinals, or maybe I think it was wildcard round or something like this, but in on-site competition, the actual problem allowed you to use each engine in one of two possible modes. Either you can use it like this, or you can swap the xi and the yi. It's still solvable in polynomial time. You need this as a subroutine. You need the observation about once you fix the decision for each of these engines, it is solvable easily. And then you somehow need to go not through all of the possibilities, which engines to use like this and which engines to use in the inverted mode, but to find some clever way of only trying some small subset of those possibilities. So the actual problem was significantly more difficult, but you needed to solve the greedy problem as a subroutine. You need to have a perfect understanding that this is what is going on. You are optimizing this area, but now instead of this vector, you may be able to use this vector somewhere there and it may be better. So you can think about the problem, and you can, if you fail to solve it, you can always just Google the editorial, which I did right. Okay. So this was one large class of greedy problems when you have to choose the correct order. By now you have seen the technique that here is a good way of thinking about choosing how to do it. Another thing, another class of greedily solvable problems are problems where you are looking for the optimal subset of things. So this is the other like standard combinatorial structure. Permutations and subsets are the two most frequently used combinatorial structures because they are the simplest ones. So how do we solve problems like this one? And this time, usually the optimal question to ask, well, let's start with a problem statement. So, this is a problem that was directly motivated by actual reality in our country. Slovakia is a country with many mountains and mountain valleys, and a lot of people have built villages in those mountain valleys, and these villages are actually in some sense linear because the valley is narrow, so usually you have one road that goes up the valley and you have houses along the road. So this is a perfect place for one-dimensional problems. You actually do have a road. Along the road there are some houses. For simplicity, we will represent them as points. And one possible problem we can solve is the problem of establishing bus stops. So the village wants to have a bus service to get into the city, which is at the bottom of the valley, and there should be some bus stops. So there will be a bus line, there will be buses coming to the village, and they will stop at some locations. And the village has signed an agreement with the bus company saying that each inhabitant of the village should have a bus stop within 500 meters of their home. Now the question for the bus company is what is the optimal number of stops you need to place into the village to make this happen? The fewer stops, the faster the turnaround time for the bus, and in a sense the fewer buses the bus company needs, so there's clearly an optimization of money. And this gives us a very simple algorithmic problem. So what you are given are the coordinates of the houses within the village in meters, and you are asked this question: what is the minimum number of bus stops you can place into the village to cover all of the houses? And this is again very easy, but it illustrates again the general technique which you can use. So, any ideas how to solve this?
You pick the first guy location and put the first stop to like 500.
Yep. That's precisely correct. So here's the first house in the village. This house has to get a bus stop. And now comes the part how we design the greedy algorithm. We need to place a bus stop to cover this house. And there is one of the placements which is clearly optimal. So we can essentially imagine us saying the phrase, we will do nothing wrong if we, and in this case, the thing where we do nothing wrong is we go 500 meters to the right, and we place the bus stop there. Why is this the case? Well, this local choice of the place of the bus stop has to be the best one, because if we now shift the bus stop to the left, we will not gain anything. The only thing that will happen is that maybe some of the houses that are currently covered by this bus stop will start being covered, but we will not gain anything else. Or another observation is that the bus stop can be anywhere from here to there, and if you wish, you can push it in the other direction. So you can start here, and by moving the bus stop to the right, you are only covering more and more houses, and you are not losing anything on the left side, because there isn't anything on the left side. So clearly the optimal choice for the first bus stop is to put it 500 meters behind this first house. And this will cover some of the houses. And now we are left with an exactly same problem as before. There is the rest of the village, and we want to cover it using as few bus stops as possible. So we can just repeat this process over and over again. Always take the leftmost house that is not covered, go 500 meters to the right, place the bus stop, find which houses you covered, and then you are done. So very easy, really solution. And the general pattern here is that even though we are looking for an unordered subset of objects, or maybe in this case it's not even a subset of objects, it is a subset of possible locations, we can introduce an order in which we look at things, and we are looking for a property like this one, that locally this is clearly the optimal choice. None of the other choices can lead to a better solution. You do nothing wrong if you locally make this particular choice. So it gives us a very easy algorithm. It can be implemented in n log n time. We just sort the array of locations, and then we go from the left to the right. And always the only thing we need to remember is the coordinate of the last bus stop. As we are processing the houses one by one, either discovered by the previous bus stop, or we need a new one, and then we compute the new coordinate and we go on. So just straight linear pass, very easy. Now, this task also carries a very practical message. The practical message is that the bus company in our story has implemented this greedy algorithm, is now using it for all the villages. And then there was this very lowly inhabited village, just a few people, a few houses here and there. So there was a house here, and there was nothing for 4 kilometers. There was a few houses next to each other, and then there was a house there. And you can all see what happened in the story. So this house got its own bus stop 500 meters from the house. This house here, this one's wrong. So the moral of the story is the customer doesn't know what they want, and it's your goal as a computer scientist to not just take the mathematical statement of the problem you got to solve. You also need to think about it, and sometimes what the customer said they want is not exactly what they say, what they want. And what they actually want is to somehow optimize the placement of these bus stops. So this then gives you a nice, a bit harder problem to think about. So you can actually augment this problem statement to not just finding the minimum number of bus stops, but given this minimum number, find such locations for these bus stops that minimize again the sum of walking distances for all the people in the village. So in this case, if there is a single house covered by this bus stop, we definitely want to have it immediately at the house that's 500 meters away. And this is a much harder problem from an algorithmic point of view, but still solvable in polynomial time. So again, in your spare time, you can think about it some more. So, new technique we just introduced is we can do nothing wrong if we choose this and this. So we are looking for locally a choice that is strictly optimal, strictly better, or well, never worse than any of the other choices we can make. Another favorite problem of mine is a problem about, well, there's a huge class of problems in scheduling. Some of them are solvable greedily, some of them are solvable in polynomial time by some complex calculations, and many of them turn out to be NP hard. So scheduling is a very interesting area. One of the easiest problems looks as follows. So imagine that this interval is 1 week of time, and during this week, the university offers a bunch of lectures, and each lecture is obviously an interval in time. Some of the lectures are long, some of them are short. And you have already made your selection, so you have a set of lectures you want to visit. And now you want to maximize the number of lectures you'll see. Obviously, you cannot be in 2 places at the same time. This could also only be done by Hermione in Harry Potter with some magical gadget. So maximize the number of non-overlapping lectures. And in some problems, there is like one obvious greedy strategy, and the only question is whether or not this strategy is correct. In this problem, there are very many greedy strategies. For example, there is a greedy strategy the one that starts earliest. So you just go to the university at the beginning of the week, and whenever a lecture starts, you go to the lecture because you want to start as early as possible in order to fit as many lectures as you can into a schedule. The other strategy you can choose, you can actually make a plan before you go to the lectures, and you can start from the shortest one. So this strategy looks as follows. So look at the list of all lectures you want to attend. You take the shortest one, you place it into your schedule, you cross off all of them, the ones that are in conflict with it, and then you repeat the process. You again, if you still have some lectures available, you take the shortest one. The reasoning behind this is that obviously you want to make the shorter lectures are better because you are just maximizing quantity. So if you choose short lectures, you will be able to fit in more of them into your schedule. Another observation might be that sometimes you can choose a lecture that has many conflicts because it overlaps many other lectures. And this is bad because it gives you very few possibilities in the future. So maybe the best strategy to choose would be the one with the fewest conflicts. And there may be also other really strategies, but the main point I want to make here now is that there are a bunch of these, and they all look kind of plausible. So if you approach this problem just by randomly guessing a strategy and then verifying it, you can deal with this problem for a very, very long time because there can be many different strategies, and for each of them you either have to come up with a proof that it works or with a counterexample. So let's try thinking about these 3. Let's start with the easy ones. So the first one, is this an optimal strategy? No. How does a counterexample look like? Early in the week, we will start a lecture. It's very long, and during this time, this is a counterexample. So you start with the earliest lecture, then you can miss a bunch of shorter lectures. So it doesn't work. Number 2. No. Again, can we get a counterexample?
One short lecture and then 2 long lectures.
Yep. Something like this is a good counterexample. So in this case, it's better to choose the 2 long lectures than the single short lecture. So again, this doesn't work. But let me stop you right now for a moment. In some cases, and for some problems, it will turn out to be the case that none of the greedy solutions you can come up with are optimal. It may be the case that finding the optimal solution is NP hard. In those cases, these greedy solutions don't have to be worthless because sometimes when we have a hard problem, we have to give up on finding the optimal solution, and this is where the entire area of approximation algorithms comes into play. So instead of finding the optimal solution, we sometimes may be able to guarantee that if you do it like this, you will get a solution quickly. It may not be the optimal solution, but it will not be worse than maybe some constant factor times the optimal solution. So maybe if the optimal solution is to go to 1,000 lectures, some of these greedy algorithms will guarantee that you will attend at least 500 lectures. So it will have an approximation ratio of 2. It will be at most twice as bad as the optimal solution. And we can go back after the lecture to these greedy algorithms and think about them also from this point of view. Can the solution produced by the greedy algorithm be arbitrarily bad? In this case, it obviously can, because instead of having this one lecture, the optimal solution can have 1 million of them here. But maybe in this case, if you always take the shortest one, maybe it will have some approximation ratio. Maybe it will come close to being optimal, or maybe not. I won't tell you. Think about it. Now we are getting to greedy algorithm number 3. The lecture with the fewest conflicts. And I think that now is a good time to have you think for a while for the last time in this lecture. So again, please grab your pens and papers and try to come up either with a proof or with a counterexample.
Você tem uma coisa?
Tem que estar pensando.
Eu tô pensando só equivalente. Do pequeno, só que tem no máximo 2 intersecções. Você não pode ter 3. Você pode ter mais caras, velho. Não pode. Que não seria o menor.
Os caras podem se intersectar também, né?
Ah, não, sim.
Não sei, parece, acho que é boa assim, mas eu não tenho certeza se a gente viu lá.
Essa é a
Você sabe como fazer?
Não tem esse.
Será que é equivalente?
Se fazer executor, tem mais quantidade de componentes. Porque isso aí é mais difícil de computar. Eu lembro que eu pedi pro Arthur fazer um contrazinho pra ver se ele conseguia. Logo,
Você vai equivalente. Pode falar. Você vai equivalente.
O quê?
Onde pegar o que acaba antes.
Não é.
Você tem um caso?
Eu acabei de fazer a análise, tenho certeza que eu só esqueci.
Tá bom,
Não é.
Qual o caso?
Não é pensado. Mas eu sei que
Mas como você sabe?
Eu tenho um curso
I
de
know for a fact.
Que é?
É script.
Eu acho equivalente, eu tô tomando 6.
Isso não era uma aproximação?
Não.
Acho que é.
Mas no caso de empate, você pega.
Tem que funcionar pra qualquer um.
Então não faz.
Que? Como assim? Como que é então? Você tem um bagulho assim? Tem vários aqui.
E
3.
posso fazer um background, acho que tem pelo menos. E esse Facebook pega. Esse aqui, esse aqui. Intercâmbio da massa.
A solução do lado seria pegar o quê? Esse cara aqui?
É, tem essa. Tem esse 3, né?
É só você
Mas os
colocar
3 é
um monte
ótimo.
de dummy.
Sim, é ótimo. Mas esse empatou com 2 todos, né?
Pegar o menor no final.
Sim, mas
Aí coloca
você,
um monte
quando
de
você pega
dummy
esse aqui, você apaga esse aqui.
no final. Um monte de cara inútil que tipo, não ia ter como você pegar.
Pega esse, apaga esse.
Um bilhete dele.
É, sempre você pega o.
Você apaga.
E apaga todos que completam com ele.
Você apaga todos que completam com ele.
Se alguém me der um lápis, talvez.
E esse
Esse
aqui
teria
vai
que
completar
apagar
dois.
todos.
Esse aqui vai completar com um só.
É que tem que.
Eu acho que aqui. Ah, aqui ó.
Aqui.
No, it's not going to work.
Você não tinha uma coisa de melhorar os gráficos? Esse problema.
Sim.
Eu acho que
É um
deve
gráfico
ser
que
equivalente.
fala, mas.
Deve ser equivalente.
Não é realmente.
Cuidado. Vai fazer, mas escreve isso daí pra explorar.
É, não.
O que você quer fazer?
Eu quero pegar uma solução que o ótimo é pegar o primeiro, certo? Qual que é a solução? Mas e eu quero tentar empilhar um monte de gente no primeiro cara.
Então, mas quando você empilha no primeiro cara, você empilha nos outros também. Porque o primeiro cara é o que acaba antes.
Sim.
Por isso que eu acho que é equivalente. Eu tô tentando fazer isso aqui, eu tô tipo pegando o primeiro cara e tô botando vários pequenininhos.
Peraí, tem papel aí.
Agora você quer essa merda.
Eu tava pedindo um papel.
Nossa,
Eu esqueci.
todo dia agora.
Todo dia,
precisa. Meu caderno de análise tá aqui. Tá vendo que eu respondo? Eu não anotei nada nessa análise. Esse é o problema. Pode anotar depois. Vou mostrar aqui, ó. Esse é o meu dar uma olhada depois da pergunta. Não, a gente responde sempre isso. O problema de cagar uma solução é de cagar uma pode até. Ah, eu vou fazer pegar outra, mas tem que tomar cuidado com a outra antes de alguma coisa.
Não sei, mas depende de como você olha pro problema.
Eu acho que é equivalente.
Não, por exemplo, pra isso aqui, tem que ser feito.
Provar essa merda, se quiser.
Isso aqui, se você não tem olhado que você olha pros outros,
Não, o ponto é, pra você está tentando cagar uma solução, mas você tem que fazer a nova solução não ser tão boa quanto a solução que você cagou. Em geral, é o que você acabou fazendo.
sim.
Caralho, fazer um papel. Acabou aí.
Cara, também não vou fazer essa produção de série que caralho.
Cara, eu tenho certeza que é falso. Eu tenho certeza que eu nunca sei acontecer. Você tem certeza? Porque exatamente é o que eu fiz. Se tiver essa situação, porque se não tem. Pegar um cara que eu sei que é falso, o cara que tinha mostrado contra ele, aí eu vou fazer contra ele, eu não consigo fazer. E daí isso te leva a acreditar que é falso. Não, mas eu sei que foi isso.
Eu sou muito ruim de pensar no fazer.
Eu já construí isso.
Sei.
Você pegar primeiro vai ser muito difícil.
É que você pode ou acabar antes do fim desse.
O que é?
O argumento de que você tem que ordenar pelo fim. Como era que era mesmo?
Eu acho que é assim, você pega a primeira vez que a solução, que o cara que você pegou não está na solução ótima. Aí tipo, esse é o cara que você ia pegar, o cara que acaba antes, e ele não está na solução ótima. Então, ou todos os caras da solução ótima estão pra frente, aí você poderia adicionar ele, então não era ótimo. Ou tem alguém que colide com eles. Não pode ninguém acabar antes dele.
Porque senão você poderia
Então,
estar perdendo espaço.
o cara que tem antes, ou o que você escolheu assim. Então, o cara que tem
Okay, time is up.
cuida com ele,
So,
passa ele.
does anyone think they have a proof?
Então, você poderia, em vez disso, escolher ele.
Does anyone think they have a counterexample?
Aí você poderia trocar.
Você meio que minimizar os problemas.
Tudo mais agora. O foda é que esse outro, a solução pode estar tipo isso. É isso.
É isso, mano. O cara é bom.
This is essentially the smallest counterexample I know of. Like you should shave off like 2 of these, but this is, you cannot get a much smaller counterexample than this. So very well done. So the point here is that this line is the optimal solution. So the optimal solution is to take these 4 intervals, and this is the only optimal solution. And now we want to trick the algorithm into not picking it. So this will be the decoy. This will be something that, yeah, pick this one. Here you have. This has very few conflicts. This only has 2 conflicts with these ones. So in order to trick the algorithm, we need to make all of the other intervals have a lot of conflicts. So we just add a bunch of intervals here and there to make sure that all of these have have more than 2 conflicts. And once we do so, the algorithm will pick this one first, and then it will not be able to be optimal. So the moral of the story is twofold. One of them is that a very easy problem statement, a very easy to describe greedy solution, and it took several minutes to find a counterexample, and only one person in the room managed to do so. So it may be, in many cases, if you just randomly guess that this may be a good greedy strategy, it may be very hard to decide whether it actually works or not. The other part of the moral of the story is that the life of the problem setter is sometimes very difficult, because as compared to the contestants who just have to come up with the working solution, when you are preparing the problem for the competition, you want to break all of the incorrect solutions. So you have to think of, in some cases, like problems like this one, where there can be many greedy solutions, you have to try thinking about them and breaking them. And also if you encounter this in a competition like Cold Forces or Top Cobra, where there is the white box testing phase, when you can submit challenges, then you have to be able to come up with such designs of solutions that break these particular greedy strategies. And this can be much more difficult than the original problem. Now, to conclude the story with this particular problem, it does have a working greedy solution, but the criterion is yet different. And we can actually discover it by using the type of thinking we did previously. So instead of so we are looking for a subset of these lectures. And we can choose them in a systematic way from the left to the right. So now we are asking the question, what is the optimal choice of the first lecture to attend? And now you have this bunch of lectures, and you are asking whether it's better to start with lecture A or start with lecture B. And if we introduce this extra notion that this is the first lecture we will be attending, this changes the game completely, because now we see that there will be a bunch of later lectures. And the most important observation now is that all of the lectures that are available after lecture A are also available after lecture B, but there can also be some other options like this one. And you can attend this lecture if you went to B, but you cannot attend it if you went to A. And the reason, the thing that makes the difference, is that B ends earlier. So if these two are our choices for the first lecture to attend, the one that ends earlier will leave us more options. So any other solution we can do with A and then something, we can also do by B and then the same thing, but not vice versa. So we don't break anything. We don't do anything wrong if we choose B over A. And the generalization of this statement is the actual greedy strategy to solve this problem. So whenever we have a bunch of lectures, the optimal choice of the first lecture to attend is the lecture that ends earliest among all of the lectures, because this is the lecture that gives us the most possibilities what to do next. So by artificially introducing the order, thinking about the leftmost choice, the first choice in time, and so on, we can then often find a greedy strategy by like eliminating all the possibilities and seeing that one of the choices is clearly superior to all the others. Okay, so I think we hit 12 o'clock, so thank you for attention. Now we will have a break for lunch.
Brasil fica bem.
A gente tem que ajudar as pessoas a achar onde almoçar, né?
Ok, cara, a gente traz só na pizza.
Oi?
Só da questão do stream aqui que vai dar certo?